Hello. In this video we're going to go over how to do the group test you guys had the other day. So we're going to start out with the first problem. We're looking at a sample of acetic acid reacted with gaseous ammonia at 25 degrees Celsius and 668 millimeters of mercury. So there are some things in here, like assuming the volume. So it says assume the volume of the solution did not change. So that means when we added in this gaseous ammonia, it's going to add into the solution and not change our volume here. And it wants me to calculate the pH and concentrations of all species present at equilibrium. So, using a hint, it says remember that when you add equations together, you must multiply the equations' equilibrium constants. And I tell you which ones you need to pay attention to. Ka, Kb, and Kw. So I'm going to start this out by just going through and solving for my concentration of ammonia. So if I have gaseous ammonia that has a volume of 2.250 liters, a pressure of 668.0 millimeters of mercury, and a temperature of 25.0 degrees Celsius, the first thing I should think is the PV equals nRT, ideal gas law. So we need to go into our ideal gas law. We need our temperature in Kelvin and our pressure in atmospheres. So to go from millimeters of mercury to atmosphere, we take and divide it by 760, and when we do that, we get 0.879 atmospheres. And then our temperature needs to be in Kelvin, so we add 273.2, getting 298.2 Kelvin. We can then put this into PV equals nRT, where our pressure is 0.879 atmospheres. Our volume, 2.250 liters. We're solving for our number of moles. Our gas constant, 0.08206 liters atmospheres, mole Kelvin, and our temperature, 298.2 Kelvin. When we do this, we solve and we get an N value equal to 0.808 moles. And we said we didn't change our volume, so it's in a volume of 0.2500 liters, giving us a concentration of ammonia at the beginning of the reaction of 0.323 molar. Okay, so we need to come up with the equilibrium expression that includes acetic acid and ammonia, and we need to use our Ka, our Kb, and our Kw. So let's start out by writing out our Ka and Kb expressions. So acetic acid, CH3COOH, reacts with water to produce our acetate ion and hydronium. That has a Ka associated with it of 1.8 times 10 to the negative 5. And then ammonia, NH3, reacts with water to produce our ammonium ion and hydroxide. Put some states in here. And this Kb is equal to 1.8 times 10 to the negative 5. And then I say use Kw. However, I'm trying to combine my equations to get the reaction between acetic acid and ammonia. So I actually want my product to be water. So I want to get rid of hydronium hydroxide on the product side by having it on the reactant side. Oop, excuse me. So I'm going to take OH minus plus H3O plus reacts to produce water. And this has a K equal to 1 divided by our KW. Right here. We want to combine these equations. And when we combine them, we multiply our K values. We cancel out our hydronium, cancel out our hydroxide, cancel out our waters, and we get CH3COOH plus NH3 goes to CH3COONH4. This gives us a K value where we multiply all of our three K's together. We're going to call this KC, and it's 32,400. Okay, if you've gotten this far, you're doing pretty good. Okay, now we're going to take this and set up a rice table to figure out how much of each of our species we have. You can, if you so choose, assume that this reaction goes to completion because of how large this Kc value is, but I'm still going to go through. And if you had done that, I would take that as correct. But let's go ahead, put in our concentrations, and prove that that is in fact what happens. And we're going to put all of this into our Kc expression, where Kc is equal to CH3COONH4, CH3COOH, and then NH3. Our Kc here is 32400 is equal to X over 0.350 minus X, 0.323 minus X. And I'm going to go over to my left and start solving. So we get 32400 is equal to X divided by 0.113 minus 0.673X plus X squared. Multiply both sides by our denominator, and we would get 3661.2 minus 21805.2x plus 32400x squared is equal to x, and then subtract x from both sides, we get 32400x squared minus 21806.2x plus 3661.2 is equal to 0. I'm going to do the quadratic equation, and what we get is an x value equal to 0.321 molar. So basically the same value as this, small enough, or it's large enough value that we can basically assume that we consume all of the NH3. So all we have left is CH3COOH, which is equal to 0.350 minus 0.321, giving us a concentration of 0.029 molar. We could go through and do a rice table for ammonia, since there is some, but it's so small that I'm going to ignore it. And we're going to go and do a rice table for our dissociation of the remaining acetic acid. And then we're going to put this into our Ka expression. 1.8 times 10 to the negative 5 is equal to x squared divided by 0.029 minus x. We're going to ignore that x, giving us 1.8 times 10 to the negative 5 equals x squared divided by 0.029. And we get an x value equal to 7.22 times 10 to the negative 4. So, real quick, this equals our hydronium concentration. And you might be asking yourself why I have thus far ignored this. But hopefully you caught on that our Ka and our Kb are the same value, which means when they react, they produce a neutral salt. Okay, so we have our hydronium concentration. We can then take pH is equal to our negative log of our hydronium concentration, 7.22 times 10 to the negative 4. And we do that, we get a pH equal to 3.14. And at equilibrium, we can make our ammonia concentration equal to 0.323 minus 0.321, which gives us a concentration of 0.002 molar. Our acetate concentration, C3COOH, is equal to 0.350 minus 0.321, which is 0.029 molar. And then we already figured out our hydronium concentration of 7.22 times 10 to the negative 4. So, there's all of our concentrations and our pH. Next problem. We have concentrated sodium hydroxide added dropwise into 1 mole or 1 liter of 0.1 molar solution of iodic acid. It's added in until we reach a pH of 1.2. So we've neutralized some amount of this iodic acid. How much? We don't know. So we have some initial concentration which I'm going to call Y. So we have some initial concentration. We don't know what it is. It's going to go and it's going to dissociate into hydronium and our iodate ion. And we want to know, using the fact that the pH is 1.20, what are concentrations of intact iodic acid and iodate ion are in solution. So, first thing I'm going to do is I'm going to take my pH and solve for hydronium concentration. So hydronium concentration is equal to 10 to the negative pH, which is equal to 10 to the negative 1.20, which gives me a hydronium concentration of, the next page, where I did this math, 0.0631 molar. We can then set up our dissociation. And we're starting out with some initial concentration of Y, or of our iodate. We don't start out with any of these. We do minus x, plus x, plus x. This gives us y minus x, x and x, where x is our hydronium concentration, so it is equal to 0.0631. Okay. Now, this, I am now going to call that concentration Z, just to keep everything in line, because I don't actually care about the initial concentration. I only care about the equilibrium concentration. So I'm going to put this into my Ka expression, where Ka is equal to H3O plus concentration, IO3 minus concentration, HIO3 concentration. So my Ka here is 1.7 times 10 to the negative 1. It's going to be equal to 0.0631 squared divided by Z, where Z is my equilibrium iodic acid concentration. Okay, so I can do some math, solve for Z, and I get a Z value equal to 0.0865 molar, and Z is equal to my HIO3 concentration. So we have successfully figured out all of our concentrations. Okay. Next problem, monoprotic acid was titrated with 0.125 molar sodium hydroxide. At 20 milliliters of sodium hydroxide, we are at equivalence. And after adding 2.50 milliliters of sodium hydroxide, we had a pH of 6.912. So I'm going to look at each of these points and basically figure out my moles of sodium hydroxide and use that to get information about the moles of our weak acid. So at 20 milliliters, or 0.02000 liters of sodium hydroxide, we are at equivalence, which means that our moles of sodium hydroxide equal our moles of our monoprotic weak acid. So from this information, we figure out that we have 0.0025 moles of NaOH, and because it's a monoprotic acid, for every 1 mole of NaOH, we have 1 mole of our weak acid, giving us 0.0025 moles of HA. So now we've determined the number of moles of our weak acid. Now we also want to look at this point right here. When we're at 2.5 milliliters, we have a pH of 6.912. So I'm going to take my milliliters of sodium hydroxide, convert it into liters, and figure out how many moles I have here. We multiply this out, we get 0.0003125 moles of NaOH. Now, this is our buffer. This is equivalence. So using these two pieces of information, I can figure out what my Ka value is by using my Henderson-Hasselbalch. So first I need to figure out how many moles of HA are left over after this reaction. So my weak acid reacts with sodium hydroxide to produce my salt and water. I know I start out with 0.0025 moles of my weak acid because that's how many moles there were at equivalence. And after adding in 2.5 milliliters, I had 0.0003125 moles of my sodium hydroxide. So I'm going to use that information to figure out how many moles of acid and base I have at this point. So when I subtract this out, I get 0.002185, and 0.003125. So I have my moles of my base, my moles of my acid. I can then use my Henderson-Hasselbalch. pH is equal to pKa plus log base over acid. I have my pH. My pH is 6.912. I'm basically solving for pKa, and I have my moles of base and my moles of acid. Using this, I get a pKa value of 7.76, and Ka is equal to the negative log of, Ka is not equal to that. Ka is equal to the 10 to the negative pKa, so it's 10 to the negative 7.76, which gives me a Ka value of 1.75 times 10 to the negative 8. Okay. Next problem, our titration. So here, I want you to give me the pH initially, after the addition of 5 milliliters of hydrochloric acid, after the addition of 12.5 milliliters of hydrochloric acid, after the addition of 25 milliliters of hydrochloric acid, and after the addition of 26 milliliters of hydrochloric acid. First step, figure out how many moles of your titrant you have. So we take our 0.1800 molar NH3 multiplied by our total volume, 0.05000 liters, giving us 0.009000 moles of NH3. Now we want our volume of HCl at equivalence. So we take our 0.009000 moles of NH3, convert it into moles of HCl, which gives us 0.009000 moles HCl. And using our concentration, dividing by our concentration, (0.3600 moles, we get our volume of 0.025 liters, or 25.00 milliliters. So this point is our equivalence. This is divided in half, so this is our half equivalence. This, therefore, is a buffer region, and this we have an excess of 1 milliliter of HCl. Okay, so now that we've gotten that, let's go ahead and start. So we start initially. So initially we have got just NH3. So it's going to react with water in a hydrolysis reaction to produce NH4 plus and OH minus. Initially we have a volume of 0.1800, and it dissociates like so. Now we can put this into our Kb expression. X squared divided by 0.1800 minus x, small x, we get 1.77 times 10 to the negative 5 is equal to x squared divided by 0.1800. And when we solve we get X value equal to 0.00178 molar, which is equal to our hydroxide concentration. We can then take POH equal to negative log hydroxide concentration, 0.00178, giving us a pH of POH of 2.75, and then we could solve for our pH by taking 14 minus our POH to give us a pH value equal to 11.25. Next, we're going to add 5 milliliters of HCl. So at 5 milliliters of HCl, the first thing we want to do is convert from liters of HCl into moles of HCl. Sorry, this is being very finicky apparently. So we have 0.00500 liters of HCl. We have a concentration of 0.3600 molar. That gives us 0.001800 moles of HCl. We've done partial equivalence, so we need to do a BCA table. So we have our NH3 plus our HCl goes to NH4Cl. So we started out with 0.00900 moles of NH3, and we have 0.00180 moles here, minus our limiting reagent, from our reactants, and add it to our products, giving us 0.0072 moles of NH3, 0 moles of HCl, and 0.00180 moles of NH4Cl. We can then use our Henderson-Hasselbalch to figure out what our POH is, but first we need to figure out what our pKb is by taking the negative log of the Kb. We get a 4.75. Then we're going to put it into our base Henderson-Hasselbalch. And what we get is 4.75 plus log base moles 0.001800 divided by our acid 0.007200. And when we solve for this, we get a POH equal to 4.15, and then we get a pH equal to 14 minus 4.15, giving us a value of 9.85. Our next step, 12.50 milliliters. That is when we are at half equivalence. And as such, our POH is equal to our pKb, which is equal to 4.75. So our pH is equal to 14 minus 4.75, giving us a value of 9.25. Next, 25 milliliters. HCl, we are now at equivalence. So all of our NH3 got converted into NH4. So we started out with 0.000 or 0.00900 moles of NH3. Now we have 0.009000 moles of NH4. We're going to take that mole amount and divide it by our total volume. We added 25 milliliters of hydrochloric acid to a total volume, or to a container with 50 milliliters of ammonia. So we have a total of 0.0750 liters of solution, which gives us a concentration of 0.012 molar NH4 plus. We are now going to put this, well, next, after we have our concentration of NH4 plus, we need to solve for our Ka, which would be our Kw divided by our Kb. And we get a Ka value of 5.65 times 10 to the negative 10. So now we can do dissociation. NH4 plus H2O gives us NH3 plus H3O plus. Solve for this. We start out at 0.012 molar here, minus x plus x plus x, and we put this into our Ka expression. 5.65 times 10 to the negative 10 is equal to x squared divided by 0.0120 minus x, small x, we get 5.65 times 10 to the negative 10 is equal to x squared divided by 0.0120. And when we solve, we get an x value equal to 2.60 times 10 to the negative 6 molar, which is equal to our hydronium concentration. So we can do pH is equal to negative log 2.60 times 10 to the negative 6, giving us a pH equal to 5.58. Last, we're at 26.0 milliliters of HCl. So we have excess 1 milliliter. Beyond our equivalents. So we can just do a dilution calculation where we take our 1 milliliter of HCl, times it by its concentration, set that equal to our total volume, and we can figure out the concentration of that 1 milliliter after it's diluted down. Oh, not 51. 76, sorry. 76 milliliters. So 76, so our V2 is the 26.0 milliliters plus the initial 50.0 milliliters, giving us a total of 76.0 milliliters in our solution at this point. When we solve for this, we get an M2 value of 0.00474 molar HCl, which means that our hydronium concentration, since it's a strong acid, is 0.00474 molar. And we can solve for our pH. And we get a pH of 2.32. Okay, last problem, we want to calculate the molar solubility of iron hydroxide with this KSP in each of the following: pure water, buffered at 4.5, buffered at 10. So here it's just a regular KSP problem, and then two problems where we are looking at common ion effect. So for A, we're taking iron hydroxide, solid, dissolving it to produce iron 3+, and 3 hydroxides. We don't care about iron hydroxide, but we start out with 0 of both of these, and then as we dissolve, we produce S and 3S, where S is equal to solubility. So how much is soluble? And we get S and 3S. We can then put this into our KSP expression. And we get 1.3 times 10 to the negative 32 is equal to S 3S cubed. And when we do this math, we get 1.3 times 10 to the negative 32 is equal to 27 S to the 4, giving us a solubility of 4.68 times 10 to the negative 9 molar. Okay. In B, we have a pH equal to 4.5, which means we have a pOH equal to 9.5, and a hydroxide concentration equaling 10 to the negative 9.5, or 3.16 times 10 to the negative 10 molar. This indicates that we have a hydroxide concentration that is lower than pure water, so we actually should increase our solubility here. So we have iron hydroxide dissolved to produce Fe3+, and 3 hydroxides. Again, we don't care about that. We start out with 0 here, and we start out with 3.16 times 10 to the negative 10 here, plus x plus 3x gives us x, and then 3.16 times 10 to the negative 10 plus 3x. That will then go into our KSP expression. 1.3 times 10 to the negative 32 is equal to, I don't know, I meant to do s, sorry. Let's erase those. S. 1.32, I don't know why it keeps doing that. 1.32 times 10 to the negative 32 is equal to S times by 3.16 times 10 to the negative 10 plus 3S cubed. We have a small k, so we can use small x, and we get 1.3 times 10 to the negative 32 is equal to S times by 3.16 times 10 to the negative 10 cubed. And then when we solve for S, we get an S value of 4.12 times 10 to the negative 4. So a higher concentration. Technically, we simplified a little too much with this one, but I accept that. What is going on? Ooh. Let us try and get through C without it screwing up too much. So our pH is equal to 10.0, giving us a pOH equal to 4, and a hydroxide concentration equal to 10 to the negative 4, which is 1.0 times 10 to the negative 4 molar. We're going to set up our equation. and we get our rice table. Zero, and then 1.0 times 10 to the negative 4 plus x plus 3x s gives us s, and then 1.0 times 10 to the negative 4 plus 3s. We'll then put this into our equilibrium expression. 1.3 times 10 to the negative 32 is equal to s, and 1.0 times 10 to the negative 4 plus 3s cubed. And when we do our small x approximation, we get 1.3 times 10 to the negative 32 is equal to s times by 1.0 times 10 to the negative 4 cubed, and we get an s value equal to 1.3 times 10 to the negative 20 molar, which hopefully we expected. We had a higher concentration of hydroxide than in pure water, so we'd expect our solubility to go down. So in the first one, we have just solubility in water, which is based directly on KSP. In B, we have a solubility that is higher than in pure water because we are at a lower pH, which means we have less hydroxide, which means we are going to shift towards our products, and that's what we saw. And then in our last one, we have a hydroxide concentration that is greater than in pure water, so we should expect our solubility to increase. Okay, that's the test. Hopefully that made sense to everybody, and see you guys later. Bye.